Hello, today we're going to be looking at circle theorems. Now most of these are probably about grade B at GCSE, probably moving up to grade A, and the last one when we get to the alternate segment theorem is probably classified as an A/A star circle theorem. You are expected to know the basics of angle relationships before you start this, so you need to understand about angles on a line adding up to 180, around a point, 360, vertically opposite are equal, angles in polygons, particularly triangles and quadrilaterals, and you're expected to know about the parallel line ones, alternate, corresponding and interior angles. So you need to make sure you understand that. Very important thing with all angle problems is to read the questions carefully. If it says explain your reasoning or give reasons, you are expected using the English language to actually explain the angle relationships you've used, and how you write that is really important. You have to get the wording correct. You can't just put working out. If it says show your working, all thereafter is showing how you get from the starting point to the finishing point. So that is working out. Let's start with just some basics, because obviously we're going to be using some of these words, some of the words related to circles. So obviously we've got a circle. If you see a spot with a little O in the middle, that means that is the centre of the circle. Of course, the distance around the edge of a circle is called the circumference. A line that passes all the way through the circle from one side of the circumference to the other, passing through the centre, is of course called the diameter. And from the centre to the edge, half the diameter, is the radius. A line outside the circle which touches the circle in one place is called a tangent. Okay, it's a line that touches a circle in one place. A tangent and a radius are always perpendicular. They're always at right angles to each other. That's a very important fact to remember, and we will come across that later on. A line, a bit like a diameter, goes from one part of the circumference to another, but doesn't necessarily have to go through the centre of the circle, is called a chord. Now, as you can see with that chord there, it's sort of sliced the circle into a smaller bit on the right hand side and a much larger bit on the left hand side. Okay, the smaller bit is called the minor segment. So a chord splits a circle into two segments. So the smaller one is the minor segment, the larger one is the major segment. You need to understand all those words. Okay, let's look at the different angle properties. So start with the first one. So we start with a circle, all right, and the key thing here, so if you're asked to explain it, this is the terminology you need to use. Angle in a semicircle is a right angle. Very basic one, this one. We draw a diameter. If we connect the ends of that diameter to any point, any single point on the circumference, as you can see there, it always forms a right angle. Okay, so if you connect the two ends of a diameter to any particular point on the circumference, it always forms a right angle. Let's look at some examples then. So we've got this triangle here, and we can see that we've got a diameter. We've got 41 degrees on one side, so obviously either end of the diameter connects to form angle A, which means angle A must be a right angle. And of course we know that the three angles of a triangle add up to 180, and if you're asked to explain it, that's the wording you need to use. The three angles of a triangle add up to 180 degrees. So we know one's 90, one's 41. We take those two away from 180, we're left with B, which is 49 degrees. Fairly straightforward example. Example 2, a little bit more difficult. Now remember, the little dashes mean they are equal lengths. Well, that's pretty obvious anyway. You probably wouldn't need to actually have those on there, because if you look at them, they all come from the centre to the edge. So they're all radius of the circle, so they've got to be the same. So let's focus on the big triangle that I've just highlighted there. Well, obviously we've got a diameter there, so either end of the diameter connects together to form the combination of angles D and E, which of course means those two must be a right angle. Now if we try and clear out from our minds all the other superfluous information, in that triangle you've got a right angle, you've got the 66 degree angle at the top, and you've got C in the bottom right hand corner. So they've got to add up to 180 because they're in a triangle. So if we take 90 and 66 away from 180, we get that C is 24 degrees.
Now, let's focus on that little triangle at the top again that I've highlighted. Notice the little lashes. That of course means two lengths are the same, which means it's an isosceles triangle. And the base angles of an isosceles triangle, of course, are equal. What I mean by the base angles are where the two equal sides start from, not where they meet. So the 66 and the D are the base angles of the isosceles triangle. And again, if you're asked to explain it, you need to state base angles of an isosceles triangle are equal, which means that D is 66. Okay, and of course F then must be 48 degrees because the three angles of a triangle have to add up to 180 degrees. So 66 and 66 is 132. Take that away from 180, you get 48. So let's focus on the other triangle that's got E, G and C in it. And notice again, we've got an isosceles triangle here. We know what C is, remember, it's 24 degrees, which means E must also be 24 degrees. And if E and C are both 24 degrees and the three angles of a triangle add up to 180, that must mean that G is 132 because we take two 24s away from 180. Okay, angle property 2. So, we draw a chord. And notice we've got a centre of a circle here, so we're drawing a chord. So remember, it's a chord, it's not going through the diameter. If we connect that chord up to the centre of the circle, we of course form an angle. Now we're going to stay in the same segment. Remember, the chord separates a circle into two segments. We've got the minor segment at the bottom, the major segment at the top. We're staying in the same segment as the centre of the circle, so we're staying in the major segment. If we connect those 2 points together to another point on the circumference, we get this sort of kite shape. Now, and that of course forms another angle. Now, if provided you're in the same segment of the circle and you're going from the same chord, the angle at the centre, which is x, is always double the angle at the circumference, y. So the angle at the centre is double the angle at the circumference. In other words, x is 2 times y. So again, let's look at some examples. Right, so we've got the angle at the centre. If you notice that you can't really see the chord there, but if you notice, angle A is the angle at the centre, which means the 51 is the angle at the circumference. Well, A must be double that, so A must be 102. And of course, A and B together, they're angles around a point, and we know that angles around a point add up to 360. And again, if you're asked to explain that, angles around a point add up to 360. So if we take 102 away from 360, we get 258 degrees for B. Right, this is a bit more complicated. Example 4. So this is where we probably need to just highlight various bits and pieces and also consider answering questions in the order that the letters are given in the alphabet. So we're going to start with C. So let's look at what we know. We know that one of those angles is 158. We know that that little angle I've marked there must be 22 because angles on the line add up to 180. Now, obviously the lines connecting, so that must mean that C is 22 because the lines connecting the centre to the 158 and the centre to C, of course, are both radiuses, which means C and 22 must be the same because that triangle is an isosceles triangle. So C is 22 degrees. Which of course means the missing angle there that I've just marked is 37 because C, that missing angle, and 121 form a straight line. So it's 180 degrees, so we take 121 and 22 away from 180, that leaves us with 37. Again, that triangle on the left hand side is an isosceles triangle because you've got two radiuses there, which means the bottom angle is also 37, and 37 and D are on a straight line, so they make 180. So that means that D must be 143. So all we're left with now is E. Well, if you look at the top, the angle at the circumference is the combination of 37 and C. So C is 22, so 37 and 22 is 59 degrees. E must be double that, so E is 118 degrees because E is the angle at the centre. Angle property 3. Angles from the same chord in the same segment are equal. Okay, right. So we draw a chord. We're not bothered about the centre this time, so there's going to be no centre marked in here. So we're sticking again to the same segment. So I'm going to stick to the major segment because there's a bit more room there. If I connect either end of that chord to a point on the circumference, it forms an angle.
if I do it to a different point, I call that angle X, do it to a different point, call that angle Y, and a different point, angle Z, and I could keep doing that provided I'm in the same segment. Now, provided they're in the same segment and from the same chord, those angles will always be equal to each other. And the way you'd explain that is angles from the same chord in the same segment are equal. So X, Y, and Z are both identical to each other. Okay, example 5 then. So first of all, let's look at the angles in the centre there. There's no centre of the circle marked here, so we can't use the angle at the centre is double the angle at the circumference or anything like that. Now, A and 83 are vertically opposite, and we know that vertically opposite angles are equal. So A must be 83 degrees. Let's focus on that little triangle on the right hand side now. Now we know what A is. We know one of the angles is 42. We know the three angles of a triangle add up to 180. So if we take 83 and 42 away from 180, we get B to be 55 degrees. Okay, right, now let's look at that 42 in detail. Let's look at the two lines that form the 42 degrees. Okay, those are the two lines. Let's connect them up, and that of course finds us the chord. Now we need to look, are there any other angles that start from that same chord in the same segment? And if I highlight it, you can see yes, there is. C. So C and 42, they're both in the same segment, they both come from the same chord, so they must both be equal to each other. So C is 42. Right, so the only angle I've got left to find is D. Alright, well I know what B is. There's B, and there's the two lines that form B, and that's the chord it starts from. Well, D and B are both in the same segment, and as you can see, they are also both formed from the same chord, so D and B are the same, so D must also be 55 degrees. Example 6. Right, remember the little arrows there mean those two lines are parallel. They're parallel to each other. So when you see that, always be thinking, right, I need to be looking out for alternate angles. You're looking for Z shapes. Corresponding angles, you're looking for those sort of F shapes where the bars are parallel to each other. So again, let's start with the earliest letter in the alphabet, E, and notice that you can see a Z shape there. So you've got 53 and you've got E. The top and bottom of the Z are both parallel to each other. So 53 and E are alternate angles, and alternate angles are equal to each other, which means that E must be 53 degrees. Right, so now we've got E. Alright, the 53 degrees is one of the angles we know. Let's look at the two lines that form it. Okay, and there's the chord that forms that. So let's stick to the segment on the right hand side, the major segment, left hand side, sorry. Alright, and look at, is there any other angle that is formed from the same chord in the same segment? Well, yes, there is. It's angle F. So F and 53 are in the same segment from the same chord, so they must equal each other. So F is also 53 degrees. Right, so let's look at that triangle now, because I want to find out what G is. I now know, remember, that F and E are both 53 degrees. I know that the three angles of a triangle add up to 180, so if I take 53 and 53 away from 180, I get G to be 74 degrees. Right, so finally I need to find out angle H. So let's look at that. So H, there's the two lines that form that, there's the chord. Okay, so let's look at which other angle is formed from the same chord. It's that one there, but of course I don't know what the angle is. So how am I going to find out that? Well, if I look at that triangle I've just highlighted, right, I know what E is. E's 53. The angle in the bottom left hand corner is a combination of 31 and F. Well, I know what F is. F is also 53 degrees, so that angle there is going to be 84 degrees. So I do know two angles of that triangle. So if I take 84 and 53 away from 180, that gives me 43 degrees, which of course we've just shown, because the angle and H come from the same chord in the same segment, they are equal to each other. Okay, our next angle relationship relates to something called a cyclic quadrilateral. Now, of course, we know a quadrilateral has four sides. Now, a cyclic quadrilateral is where the four vertices of the quadrilateral actually touch the circumference of the circle.
Okay, so that's an example of a cyclic quadrilateral. Now, we already know that the four angles of a quadrilateral must add up to 360 degrees. Well, specifically for a cyclic quadrilateral, also opposite angles add up to 180. So, for example, angle A there, opposite that we've got angle B, they have to add up to 180 degrees. Then we've got angle C there, opposite that is angle D, they must also add up to 180 degrees. Okay, let's look at some examples. So we can see we've got a cyclic quadrilateral there, and what we can see there is opposite angle A, you've got 180 degrees, they've got to add up to 180 degrees, which means A must be 72 degrees. Opposite angle B, you've got 78 degrees, again they've got to add up to 180 degrees, so B must be 102 degrees. Okay, example 8 then, slightly more complicated. Now we've got a number of quadrilaterals here, as you will see later on. We've actually got 3 quadrilaterals, but only one of them is a cyclic quadrilateral. And I've highlighted the cyclic quadrilateral there because that's the only quadrilateral where all 4 vertices touch the circumference of the circle. Now at the moment it doesn't look like we've got a great deal inside that quadrilateral that's going to help us, because the opposite, we've got the E and the 71, opposite that we've got 31 and D, we've got 2 unknowns there, and the other 2 angles we don't know at all. However, if we look at the bottom, we've got 62 degrees there, and that makes an angle of 180 degrees with the bottom angle of the cyclic quadrilateral, because they're on a straight line, and of course that helps us to find the top one. Now, you might think, why do we need to do this? Often with the more complicated questions, it's useful to actually work out every other angle you can possibly do from the information you're given, even the blank ones that aren't, haven't been lettered or anything like that, because that will give you some help later on. So now we've got 118 degrees, we can work out the angle at the top, because it's opposite it, it's 62 degrees. And the reason that helps us is that, of course, if you think back to a previous angle relationship, that's the angle at the circumference, C is the angle at the centre, so C must be double that, so C is 124 degrees. Okay, right, now then, if we look at that one, now we can see that's not a cyclic quadrilateral, it is a quadrilateral, but C doesn't touch the circumference, it touches the centre, so it's not a cyclic quadrilateral. But of course we now know the 118 degrees, we knew 71, we now know C, so we know 3 of the 4 angles inside that quadrilateral. We take those away from 360, it leaves us with D, which is 47 degrees. And if we look at the kite shape, again that's a quadrilateral, it's got 4 sides, but again one of the vertices is at the centre, not at the circumference, so it's not a cyclic quadrilateral. We know 62, we know 31, we want to find E. We don't know the 4th one at the moment, but that's quite easy to find, because combined with C, it's around a point, it must add up to 360 degrees. We know that C is 124, so that missing angle must be 236. So if we take those 3 angles away from 360, we're left with E, which is 31 degrees. Okay, next angle property involves tangents. Now we've met tangents before, that's a line outside a circle that touches a circle in one place. Now let's put 2 tangents onto this circle. They touch the circle at A and B, and the 2 tangents themselves intersect at point T. Now, when this happens, if you've got 2 tangents from the same point, then the distance from where they intersect to where they meet the circle are actually the same. So TA and TB are equal to each other. Now we also know, of course, because we met this right at the start, that of course they're from their centre, their radiuses I've just put on there. So OA and OB are radiuses, and of course we know that tangents and radius always meet at a right angle. Right, okay, so let's put that into action with this next set of examples. So example 9. Right, so we've got this triangle here, we've got a tangent there, part of which is the length C, which we've got to find length C, we've got to find angle A and angle B. Well, O to A, of course, is a radius, which means it meets a tangent at a right angle. So angle A, straight away, we know is 90 degrees. Now remember, we've got those little dashes, that means those lengths are the same. So lengths, of course, we've got to think of something else other than angle relationship. So right angle triangles, that you should be thinking Pythagoras or trigonometry.
Well, we know that obviously we've got one length which is 4. The hypotenuse of the right angle triangle, if you see, is made up of 2 of those equal lengths, so the hypotenuse is actually 8 centimetres long. So we can apply Pythagoras' theorem, where C is one of the shorter lengths which is missing. Well, first of all, let's go to B. So obviously we've got 3 angles of a triangle add up to 180 degrees. We know A is 90, we know the 63 at the centre. Take those away from 180, we get B to be 27. So let's go back to Pythagoras. So we've got one of the shorter sides is 4, the other shorter side is C, we don't know, and of course the hypotenuse is 8 because it's made up of 2 of those equal lengths, so 2 4s. So square everything. The numbers are on different sides, so we take the difference, we square root, and we get C is 6.9 centimetres. Example 10, much more complicated. Right, so first of all, we know that D is 12 because it comes from the same, there's 2 tangents there. Okay, we can see the bottom tangent intersects with the circle, it's 12 centimetres, so that must be the same as D. We also know we've got a right angle triangle there, okay, because we've got a radius and we've got 28 degrees, so what that means is if we take the 90 and the 28 away from 180, we're left with E to be 62. And if you think about it, that means that the other right angle triangle is identical to the one we've just looked at. So the E, 28 and 90 is the same as the one including F, which means F must also be 62 degrees. They are identical right angle triangles because if you think about it, they both have the same length, 12. They both share the hypotenuse, so they're the same. They both have the same radius, so they've got 3 identical lengths. Okay, so they've got to be the same size. Right, and G is 62. You can see that the angle at the centre is a combination of E and F. So E and F together make 124. G must be half that, so it's 62 degrees. Okay, the final angle property involves the alternate segment theorem. Now this is the sort of A star bit of circle theorems. You don't get this very often, but this will tend to be at the back end of your exam paper. It's not particularly difficult, it's just difficult to spot. It's quite difficult to explain as well, but once you get your head around it, it's really quite simple. Right, so we've got the alternate segment states that the angle between a tangent and a chord is equal to the angle formed by the chord in the alternate segment. Okay, right, so we're on about the chord in the alternate segment that's connected up to the same point. So we look at that one, that's the angle between the chord CD and the tangent AB. Now from the same point C, the chord in the alternate segment is CE, which means the angle at the top there must be the same. So angle ACD equals angle CED by the alternate segment theorem. Similarly, if we look at the other side, so we've got the chord, the angle between the chord AB and the tangent AB and the chord CE, so it forms angle BCE. Well, from the same point, the chord in the alternate segment would be chord CD. So look at the angle there; those two angles are the same. So again, angle BCE equals CDE. Okay, let's try and explain this with a couple of examples. Right, so we've got this here, so we've got quite a few angles to find here. So first of all, there's the angle between a tangent and a chord, the point of intersection, 24 degrees. Now, the chord that's connected up to point C, that's in the alternate segment, is the chord that connects C and D together. So in other words, it's angle F. So F and 24 must be the same as each other. Similarly, on the other side, we've got G there, that's the angle between the tangent AB and the chord CD. Well, again, from the same point C, the chord in the alternate segment is CE, so that means that it's the 63 degrees, and G must be the same. And of course, now we've got the two angles of that triangle inside the circle, we can work out the third angle, because the three angles of a triangle must add up to 180. Okay, so H must be 93 degrees. Of course, the other way we could do that is we know that G, H and 24 are 180 degrees because they're on a straight line. So there's two ways of actually finding that. You should get the same answer whichever way you use. Right, final example then. Example 12. Okay, right, so if we look at that triangle first of all. Now, if we think back to the previous angle relationship, we've got tangents there from K to L and from K to J. So in other words, they start from, they intersect at point K, so KL and KJ must be the same length, which means the triangle that contains P, N and 88 must be an isosceles triangle. Now of course that means the base angles of an isosceles triangle are equal. Well, the base angles are the two which start the equal side, so N and P are the base angles. So if we take 88 away from 180, that leaves us with 92 degrees. Divide that by 2, we've got P and N to be 46 degrees. Right, so now if we just highlight that little bit there, that's going to help us with the alternate segment theorem. And if we look at N, okay, so that's the angle between the tangent and the chord JL. Well, the chord that starts from J and is in the alternate segment is J to M, which means angle N and angle Q, must be the same. So Q is also 46 degrees. Now, of course, we've got a quadrilateral there, but Q is the angle at the circumference, R is the angle at the centre, so R must be double Q, so it's 92 degrees. And if we focus on that triangle there, well, O to J and O to L are both radiuses, so they've got to be identical lengths. So again, we've got an isosceles triangle where S and T are the base angles. So if we take 92 away from 180, divide it by 2, we get S and T to be both 44 degrees.